Thanks, Christian. Okay, well, thank you all for coming to see my talk this afternoon, and I'm looking forward to spending a couple of weeks here. So as Christian said, I'm talking about some ways to do astrophysics with potential gravitational wave observations from something like advanced LIGO. And the particular astrophysical problem that I'm going to be interested in is the structure and size of neutron stars. So I'm going to start by giving a little bit of background as to one of the fundamental sources of uncertainty when it comes to learning about neutron stars. And but I'm also going to point out, because in the last several years there's actually been quite a large decrease in the amount of uncertainty commonly accepted for the equation of state of neutron stars. So if you haven't looked at them lately, we're actually, as a scientific community, making progress in understanding what the equation of state actually is. But in summary, the matter in neutron stars is compressed to something like 10 times the density of a nucleus, up to, which means that the properties of matter at that density are not something you can detect directly in a lab. In a neutron star, at least as it inspirals, the matter is in a ground state. It's effectively cold. And you have a many-body interaction problem, and the interactions are coming from nucleon interactions, residual QCD of the protons and neutrons. And as the density in the neutron star increases, as you go towards the center, protons and neutrons may no longer be the favorable degrees of freedom to describe your theory. You can have things like a transition to quark matter. So there's a lot of possible stuff going on, but one thing that's come out of the last few years is this large number of candidate equations of state have started to be constrained both on the theoretical side. So this thick blue bar is coming from improved modeling of nuclear interactions from chiral effective field theory, which I won't talk anything about. But as you can see, this is something that's changing the range of pressure at a few times nuclear density from something that's almost a half an order of magnitude to something that's on the factor of a few. So this is quite interesting. But there still remains a substantial swath, especially at the high densities, of potential variation in the pressure-density relationship of matter at this density. And this is something that we probe astrophysically when we make a measurement of a neutron star. So this pressure-density relationship, as you integrate out from the core of the neutron star, determines the structure that gives you properties like the overall mass and radius of a given star and how those two relate together. So this is a very common thing to do, is to translate from some pressure-density relationship into a particular mass-radius relationship. And then you can also consider other properties, such as the moment of the inertia as a function of mass, or the tidal deformability as a function of mass, which I'll talk about later. So properties like the radius, then, are something that we can use if we make a measurement. We constrain this swath of potential mass-radius relationships to be the ones that go through, for example, a star of a given mass measured to have a given radius. So we restrict this space of underlying pressure-density relationships to the ones that are compatible with the observation. And so observations of neutron stars are then potentially interesting in that they tell us about the fundamental properties of dense matter as it interacts. And one nice recent astrophysical example is coming from a combination of several electromagnetic observations. So this is work by Andrew Steiner as well as Latimer and Ed Brown. And by combining three X-ray bursts, thermal emission from transient low-mass X-ray binaries, and the cooling curves of an isolated neutron star, feeding all this in to what this would require for a radius and mass to be compatible with all those observations simultaneously, you have some dependence on certain modeling parameters of the outer surface and where the bursts are coming from, but we're starting to get an understanding of the radius of sort of standard mass neutron stars, the canonical value being 1.4 solar masses, that is a lot more strongly constrained than it used to be. So this is something that we're learning more about from the electromagnetic spectrum, and these are primarily things that are coming from bursts from the surface of a neutron star. Now the interesting thing about gravitational observations, though, is that they are most sensitive to the densest matter at the core of the neutron star. Anything that's going to actually perturb the gravitational field around it has to be the dense matter. So the outer layers, the crust, which have their own complicated physics that induces a lot of systematic error, the crust and the atmosphere around the star, in something you're measuring electromagnetically, does not, the gravitational potential is not affected by this, since those aspects are several orders of magnitude less dense than the matter at the core of the neutron star. So this allows gravitational wave observations to be a very complementary probe of the physics that you can get in these things. So let me then say what I'm going to focus on particularly in this talk, because this is what I've been mostly working on, is the gravitational waves from merging binary neutron stars. I should say that many things that I'm going to talk about have analogies in, say, a mixed binary system of a black hole and a neutron star. Particularly Ben Lackey, also at the University of Wisconsin-Milwaukee, has been working on that. But I'm going to particularly focus on double neutron star binaries in this talk, since those are the simulations that I've been using data from. So we expect to see some number of these in advanced LIGO that is non-trivial, that is large. The estimates vary. And for the purposes of this talk, I'm going to try and focus on something that's perhaps the loudest 1% of signals that advanced LIGO would see. So this is definitely an optimistically loud signal over, say, a several-year run, but it's not implausible. And there's so much scaling depending on what distance you actually see things at that this makes interesting, but an interestingly possible, but still also interestingly physical source of astrophysics. So for this sort of canonical system, optimally oriented, it's at 100 megaparsecs away. This is something that in initial LIGO is not a strong signal. So that's something that is stronger than, or that is strong, but not so strong that you would expect to see it in initial LIGO. But with advanced LIGO, this is something with a signal-to-noise ratio of about 30. So there's not a question of detecting this. For detection, you can do pretty much anything, and if you have an SNR of 30, well, not anything, but this should not be something that you're really having to dig down into the noise to see. This should be the loudest thing glaring at you. And if you have something like the Einstein telescope, which I'll occasionally refer to, if you don't know, this is a European proposed third-generation gravitational wave observatory, partly driving science cases to go beyond what's in progress and see where we would want to direct our next attempt at probing gravitational wave physics. And so this is sort of the standard post-Newtonian in-spiral, which is a perfectly good description for most of the signal. You can go a little bit beyond this by looking at a leading tidal contribution to the in-spiral. So this is implemented relativistically by Ina Flanagan and Tanya Indra here, and we did some further work together extending that to realistic equations of state. But the upshot is that the leading tidal contribution, the first order one, is only a valid description of the full signal up to something like 450 hertz. And generally in this regime, you have a possibly small signal-to-noise contribution, but not something that's particularly large. And then the other thing that we want to look at is numerical waveforms. So these are the gravitational waves extracted from a set of numerical simulations with varying equation of state. So the radius in these particular candidates varies from about 10 to 15. So the green one is a bit optimistically tidal. You can see by it dramatic departure there. And so this length of signal starting at around 700 hertz has a total L signal to noise ratio of about 2. So this is not something you can detect alone, but given the trigger of a loud-in spiral, there's definitely a lot of structure here that would be interesting to attempt to tease out. But to do the most physics with the available signals that we get, the real challenge is going to be connecting these two regimes. And so this is probably something I won't have much time to talk about, but is definitely a challenging proposition that's really required if we want to understand the most about this signal in the end. Okay. Let me start by just outlining the tidal deformation itself. So if you have two extended bodies in orbit or free fall, so the first order behavior is the path of free fall or the orbit. The next residual gravitational effect is the tidal deformation that's pulling the tidal bulge toward this part that's closer toward it. This part gets left behind. And the deformations that we're going to be interested in are the ones that themselves are inducing changes in the gravitational potential. So we can add a perturbative estimate of how much the gravitational potential changes for a given mass ratio and equation of state to the energy balance waveform that you get from a post-Newtonian perspective. So the tidal deformation itself you can do by just modifying a spherically symmetric model of a neutron star, and you induce a perturbation on the star of the harmonic form, the Y20 form. So this is something that's got this symmetric extension on the axis towards the other star. And generally, in that perturbation, you can look far away from the star and look at the terms of the field that are falling off like a quadrupole, and also the inextricably linked term that comes from that perturbation that acts as an external tidal field far from the star. And the ratio between these two terms is a single number that characterizes the ratio of the size of the quadrupole deformation far from the star to the strength of the external tidal field. And it's related strongly with the radius to the fifth power, so it's mostly determined by the radius of the star, so it's the size parameter. But it also has this love number, which ends up measuring something like how centrally condensed the star is. So for example, if you have a star that's got a very large radius, but the outer layers are not dense, the tidal deformation that deforms those outer layers a lot is not going to have a substantial contribution to the gravitational potential. So this is how we determine how much the potential radial, how much the size of the star and its deformation is translating into actual effect on the gravitational field. So this function this parameter, the tidal deformability, is a function of mass the same way that radius is. So you can imagine the same way that you took radius as a function of mass and mapped that back to the underlying pressure-density relationship. If you make a measurement of the tidal deformation, you could then map that to the underlying pressure-density relationship in the same way. Another nice thing about this parameter is it's identically zero for a black hole. So this is really something that measures the signature of matter on the gravitational wave. It's the difference between a neutron star, which has some finite extent, and a as collapsed as possible black hole. Okay. So then this correction is then is incorporated into the post-Newtonian waveform. And you start with the standard energy balance method. So you balance the energy of the system as a function of the separation. So x is the post-Newtonian parameter characterizing the separation of the stars, with the luminosity also as a function of the separation. And at each point in time, the separation of the system is evolving based on the speed of the luminosity. So this can be expanded up to high post-Newtonian order, and we add in this quadrupole deformation times the tidal tensor coming from the other star, and similarly, each star orbiting around each other has a tidal bulge tracing the other star, and as they orbit around each other, each individual tidal bulge is adding an additional quadrupole moment that adds to the underlying orbital system's quadrupole moment. Okay. So this is actually something that is interestingly formally fifth post-Newtonian order. So this is a higher order than we know the underlying gravitational wave general relativity description for. But this lambda having the r to the fifth term, and this m to the fifth in the whole term at all, as in the entire term, means that this effectively becomes the power of the radius of the neutron star divided by the orbital radius to the fifth power. So as the star's separation becomes comparable to their radius, this ramps up very quickly. And this is how, if you calculate it, you can actually see that this will overwhelm formally lower post-Newtonian contributions to the phasing at relatively high frequency. So you can put all this into a model for the waveform, which Tanya did, and compare this to and calculate the modifications of the waveform with this lambda parameter for each system. And this gives you an expected error. So using a Fisher matrix calculation, you can get the expected error of a measurement for this system. And these are all the error around lambda equals 0. So for the Einstein telescope, for example, of a this is a binary system of 1.4, 1.4 solar masses, you're measuring lambda with an error of about 1. And then for advanced LIGO, however, this is basically something that you wouldn't be able to measure. One caveat, though, is we restrict ourselves to the portion of the waveform that's clean, where this is actually an accurate description. We expect it to be an accurate description of all the matter physics that's going to come into that's going to contribute to the phasing. So we restrict ourselves to below 450 hertz only, and that turns out to be a strong constraint in terms of translating this into something that actually makes a measurable difference on the signal. So what I'm going to spend most of the time talking about, sorry, is there a clock anywhere? Oh, okay, good. Ah, wonderful. Thank you. Okay, so what I want to spend most of the time talking about is what happens, or how we can start to do analysis of the messier signal that you get in the merger of the two neutron stars. So this is a region that is accessible only by numerical simulation. There's definitely more than just the leading order contribution of tidal effects coming into this kind of thing. And you also see that there's these peaks in structure here, which I'll actually go into more in a bit. So this is a very messy region of of the gravitational wave signal from two binary neutron stars, which has sort of the advantage that there's potentially a lot of physics to be learned from it, and the disadvantage that trying to extract what signal property is translating into what underlying physics is also correspondingly more difficult. But one way we can get around the complexity is to look at sort of the underlying characteristics of the matter in a systematic way. So what we've been doing is varying the equation of state in a sort of phenomenological way that's physically motivated, and that this type of description can capture realistic equation of state properties. And our choice of parameterization is actually a bit out of date now, given the recent results that I talked about at the start of this, since we started planning out these simulations a couple years ago. But fortunately, most of these are actually still compatible with the observational constraints. So the region that's actually most likely, if you look at the electromagnetic region, is something like something around from B to slightly somewhere between H and 2H. I'm going to actually focus mostly on B, H, B, H, and 2H in what I present today. Yeah, So it's a bit counterintuitive, but there's a. It's actually not a very good choice of convention. Well, so you typically you talk about things that are higher pressure equation of state of being stiffer, and the ones that are softer are the ones with lower pressure. But so that's sort of the general motivation. But stiffness and softness is often used more for the adiabatic index than the actual pressure scale, and we vary the adiabatic index and indicate it with primes. So anyway, I'm mostly going to be talking about these when I present example pictures, but the full collaboration I'm talking about is covering varying, for example, the pressure scale, varying the adiabatic index, the slope in this core region, and so what we can hope to do is, well, we can hope to do various things, but we can either hope to find some physically motivated parameter, such as lambda, that perhaps characterizes the numerical simulations well also, which isn't unheard of in sort of physical things. Or we can go directly back to these underlying equation of state parameters and talk about constraining them directly, which is messier, and it requires significantly more numerical accuracy to be able to disentangle two parameters from noise instead of just one. But yeah, so we've started doing this. We have the systematic variation of the equation of state. This is a fairly large collaboration using both the SACRA code, which was originally developed in Masaru Shibata's group, and the WSGI code that's coming out of AEI, as well as several other places that I'm not going to remember to list them all. And some of the lead of actually running the codes have been Luca Baiati and Masaru Shibata, and Kaisuke Taniguchi provided the quasi-equilibrium data, and we have a wide assortment of other people working all together on this. And so the result is, well, so the setup is that we're going to take this range of equations of state and focus on an equal mass binary of 1.35 solar masses, which is pretty much as average of a system as you can expect, and for binary neutron stars is actually good to simulate the average system, because the observations don't range too far away from that in the actual examples of double neutron star binaries we have. And we use non-spinning, which is pretty good approximation for neutron stars. Also, the magnitude of a neutron star spin is going to typically be much lower than something that's going to affect the waveform. So, unlike the black hole case. Well, let me see. I know it is unimportant up to, I believe, a couple hundred hertz. Yeah, so spin frequency is, so spin becomes more important, or spin is more important than, say, tidal deformation at lower frequency. Spin, because its frequency dependence is lower. The dependence, or the strength of the term on the magnitude of the spin itself is, I think, so realistic. I think the observations of actual neutron stars in binaries have very slow spins, like a second or something like that. Do you? Up to milliseconds. Yeah. I'm sorry, I'm not remembering anything useful, but or like if you can, run that in, and the amount of spin required to make a significant contribution, more so than tidal at the end, is very high. Not breakup high, but these are old neutron stars that are going to be in these things. So. Anyway. Okay, and this is, so this is then the resulting spectra that we get. And so I showed at the start the overview showing the whole sort of range of the in-spiral. I've zoomed in on the lower right corner now. So this is the edge of the broadband advanced LIGO spectrum. This is a narrow band. The Einstein telescope is down here, and so you can imagine this sort of continuing up over to there, and this doing sort of the same. And I've just focused in on the area where we actually have information from the numerical. Information from the numerical simulations, which in this particular example is starting at around 700 hertz. And so what you see is that we do have something that looks, there's some noise, and part of that is just the effect of a finite time Fourier transform and other things. But we have something that has a systematic drop-off here from what you would expect with a black hole. So this is a phenomenological black hole fit from Lucia Santa Maria, who's now around here somewhere, but not here immediately today. And if you look at the neutron star, the largest neutron star, the 15-kilometer one, is this green one. The smallest one is this red one, and then there's some intermediate things. So you have fall off that gets larger with the neutron star, and then you have these spikes. And these spikes are what happens when, instead of collapsing immediately to a black hole, the merged object has something that is supported for a time scale, or for a period, by differential rotation as a hypermassive neutron star, which typically develops a bar mode, so has some emission of gravitational waves in a particular frequency, and lasts for some amount of time, which we do not have an accurate handle on with simulation yet. So the height of these peaks is not something that you should take as physically meaningful, but the location of them seems to be pretty well, pretty robust within the within most of the things we have looked at. And the property that if you have a large neutron star, you have something, this post-merger oscillation peak. If you have a smaller or softer neutron star, you get a prompt collapse. Larger and smaller here refer to radius. In terms of mass, it's the other way around. If you have more massive star, then it's more likely to collapse promptly, or a smaller radius star, it's more likely to collapse promptly. Something else to notice is, even if it collapses promptly to a black hole, it does not look the same as a binary black hole would. the amplitude, this is roughly the ring down frequency of the combined object, an object of the combined mass. And this amplitude is much smaller for neutron stars, which get smeared out basically as they merge together, than for two black holes.
So the initial
Yeah, well, it is not well described by the first order contribution from lambda. It is possibly,
there's more structure?
there's more structure. It scales with lambda. The bigger the lambda, the bigger the drop off, but you cannot analytically predict it at this point. Right now, we're working on trying to do that, but this is, you notice this is beyond the range where you expect lambda to be a sufficient description by itself. And trying to accurately determine whether you have some small high order effect or whether you have some small amount of numerical error that is accumulating over the long length of your simulation. At this particular frequency range, you're trying to, say, distinguish a curve and a line that are both flat enough that they can sort of map into each other. So trying to confirm that this is a tidal effect due directly to lambda is not easy. And also there's possibilities that it could be other things, such as if the neutron stars approach resonance, an F mode, so as the orbital frequency approaches some mode frequency of the star, that also can bleed off energy into exciting this mode, and so that gives a characteristically different contribution to the phasing, which also gives a drop-off. And you just have also that at some point the two stars crash together, and that dramatically diminishes the amplitude of the gravitational wave immediately, and that also leads to a fall-off. So there are various things that all have this kind of amplitude. And one thing to actually point out also is that although it is nice to plot the amplitude of the gravitational wave to look at the differences, you can have two things with very slowly accumulating phase difference that have almost the exact same amplitude, but yet can be noticeably different when you try and align them. So yeah, it's. Between this one and this one?
Right, I mean, the one is extremely.
Yes. Yeah, actually, and probably the best way to do that is actually just show some examples. So, so hold that question for a while, because it'll probably be easier for me to explain what's going on when I actually show the waveform. So the level of agreement that we've gotten with the different simulations now is surprisingly good, actually. So this is three waveforms from two codes at 3 different resolutions. These all had the same initial data, but and so if you align them at the start, you do get some decoherence, but we know that we do better at resolving the merger, since it's moving more quickly. There's less time for things to bleed away and lose small bits of angular momentum as you painfully slowly evolve these things around in almost circles. And all I've done here is align these by picking a single point where the amplitude is at the maximum. So this is a physical characteristic that we can actually trust in neutron stars. We don't have the known kind of properties of black holes that we can compare across all different equations of state. So we take the peak amplitude and we set that to be a time equals 0, and this is the plus. So that means this is a phase of, pick your convention. The phase is aligned for all the waveforms only at this single point. And then looking back, we have a very small amount of accumulated phase difference to the start of the waveform. If we include, so this includes some lower resolution simulations. sort of a couple lessons here. The farther back you want to accurately go, the higher the resolution needs to be. The smaller your neutron star is, the higher the resolution needs to be. This is not really surprising, but makes it difficult to compare between two different equations of state when the resolution required to get a given level of accuracy changes with the equation of state you're simulating. Anyway, but still, our best long resolution waveforms are getting now many orbits of pretty good phase agreement. So,
Is that
no, this is, I believe adaptive mesh refinement is incorporated into both codes in some way or another. For details on the codes, there's a very nice paper comparing whiskey and sacra by Luca Biotti and Masaru Shibata and some other people. And they go through in that paper, they have a nice layout of how the codes are the same, how they differ, and what the actual details of the implementation are. But everything here, it's hydrodynamics with high resolution shock capturing and adaptive mesh refinement and all the sort of state-of-the-art whiskey style BSS in gravitational wave evolution. One thing to mention is that it is typically harder to get the level of convergence once you have hydrodynamics in there that you would if you had pure vacuum. So this is something we require. And anyway, and as you so we can get fairly long in spirals. And looking at the merger, this is where I can show you sort of the qualitative difference you get in the waveform. So the in-spiral looks qualitatively similar for all of them. I'll talk a bit about differences later, but there's sort of two things that can happen at merger. So one thing is that it can, this is roughly the time of peak amplitude is when the two stars collide together. The frequency continues to rise up till this sort of minimum amplitude. And then after that, this is the formation of a bar mode, which actually stays stable at this oscillation frequency with some beats for tens of milliseconds. So this is something that shows a lot of spikiness and structure in the Fourier transform. And that's mostly coming from this post-merger portion. And you see the same thing here. Something interesting is that for this particular case, the whiskey code is enforcing purely cold equations of state, and the Sacra code is implementing an effective thermal component that is that's adding temperature. And they still have very similar merger dynamics, at least for a while. There's some messiness here, but the two longest ones don't actually decohere for quite some time. So that is impressive, considering we are only aligning at a single point. We weren't actually expecting the merger to agree this well between the codes and properties. This is an example of something that had this nice smooth, so it had a fall off and then a little bump at the end. So this is something, the stars crash together, the frequency continues to accelerate and then, or to sweep up, and then they basically collapse immediately to a black hole, which rings down in this little blip. So anything that has not sufficient pressure to support a differentially rotating object will look something like this, and if you get something softer, more compact, this will become smaller and smaller. Okay, so this is something that has a very small blip. This is a large blip, and these have these three, which well, so the range that's compatible with electromagnetic observations is basically from somewhere between the green and the light blue, and down to the purple. So there's still a significant range there of different type of gravitational wave structure. Okay, so we would like to actually make an explicit measurability estimate for this, or we would like to construct a scenario where we can actually measure these differences that we observe in the waveform. And so there's an ideal scenario which goes something like this. We've detected a strong waveform from using a post-Newtonian template in the early region. This should be perfectly fine. And we would like to be able to compare this with a hybrid waveform where we construct an analytic waveform from the tidal contributions that's connected to the numerical inspiral so that we know the phase tracking from the very start to the very end of the waveform. The early PN is going to dominate the alignment of the waveforms because there are cycles and cycles and cycles and cycles of early PN that you cannot knock out just because the end goes a little crazy. But then this late end spiral merger, the differences integrated against some candidate should, over the noise curve, should determine A, whether two candidates are distinguishable. Whether you integrate one against the other, do you get something that's notably different from integrated against itself? And then presumably if you get the right one, you would get a better match with whatever you're observing. To explicitly calculate, say, a measurable parameter, you have to parameterize the system. So as I mentioned about equation of state parameters, you can also parameterize by the radius. I'm mostly going to talk about lambda, but because this has this nice property of connecting smoothly to the early post-Newtonian part. But in the description of the waveform itself, there's no conclusive reason to prefer one over the other yet. There's no obvious improvement in the description of the differences between the waveform if you use one parameter versus another. They're very similar. Okay, so this was the first version of this. So this is a paper that I worked on a couple of years ago. And at that point we had fairly short waveforms, so we only and we didn't have the full post-Newtonian description, or at least I didn't have the full Pn plus lambda description. So we matched everything to point particle, and we just looked at the variation from the end. And then, so this was only really variation above 750 hertz, which was even possible given the start of the numerical waveforms. And we made some sort of order of magnitude estimates, knowing that we were neglecting this whole part of the region below. Okay. So I would have liked to be able to do something with hybrids, but that's difficult. So what we can do, though, to avoid the difficulties in constructing robust hybrids that do not suffer from systematic errors, is to just take our numerical waveforms, weight them by the noise so that parts of the numerical waveforms that are invisible do not contribute, and slide them against each other to minimize the correlation. Okay, so we actually do this in the time domain, but it's mathematically equivalent to the inner product that you use in a detection or in a search. Okay, and we minimize over the range of the waveform the difference between the waveform and an underlying base model. So the underlying model is a very long HB waveform. So this is this is sort of the underlying level of error that you have in this procedure, because all of the things that we're matching here are HB waveforms. They should all be identical. For numerical reasons they are not, and so we get some cluster. More low resolution ones tend to be further away. But this gives you at least a by eye estimate of the sort of level of uncertainty. Then you can see what happens if you do the, so this is actually a really low one, ignore that. So if you look at the smaller radius, the best you can do is still shifted a bit further away. That seems pretty trivial, but you get a bit of a larger effect if you look at a larger radius object. So H, and particularly 2H, the best you can do still has this, this peak amplitude time significantly before the peak amplitude of your reference waveform. Okay. So the nice thing about this, though, is, okay, and this is sort of a comparison of the length of the waveforms we now have compared to what we had when we did the first study. So the nice thing is we sort of can tell if the parameter is fully describing the changes in the waveform. This is, so we estimate measurability, the expectation value in the variation in some parameter at the average between 2 points by taking 1 over the square root of the inner product of the difference between the waveforms at one parameter value and the waveforms at the other parameter value. This is a discretized version of a Fisher matrix estimate of measurability for a one parameter system. We do not have an analytic description of the results of numerical simulations. So we cannot take derivatives in the sort of normal sense that you would like to calculate this kind of thing. So you have a coarsely sampled space with a set of parameters that are samples equation of states. And what you get is something that you would expect to have a linear relation, or you would have, if the difference in lambda is small enough, you have a linear relationship. And then as the difference gets bigger, you have something like this. So this is what we would see if, and so I'm generating this using the post-Newtonian waveform plus with the leading order tidal contribution over the lambda of simulated equations of state. So what you see then, if you do this with the numerical waveforms, is that the shape is similar enough that lambda seems to be a pretty good parameter to describe this result. One thing is that we have a lot of low resolution numerical waveforms. So this gives you differences that are larger than, these are just selecting the high resolution waveforms in the red here. And then scatter above them is the kind of noise you get from low resolution waveforms. But it actually looks like lambda is not a bad parameter to use to characterize the differences in these numerical waveforms. And this is not something that we would definitely expect, because there are several higher order things that we know are making a significant contribution. So some of the scatter, actually let me, so this translates into sort of a range of estimates from over different radiuses. So really this is all the same measurement, where you have approximately plus or minus 1 kilometer in broad pattern advanced LIGO and a tenth in the Einstein telescope. And the systematic errors you can get by looking you can look at varying the equation of state as, you can look at varying the numerical simulation for the same equation of state as another parameter and marginalize over it, or you can do various things that explicitly estimate the systematic error coming from numerical variation, and that's on the order of 0.1 or 0.2 kilometers. There are other sources of systematic error. So if you measure something, you slide one of these numerical waveforms against it, you get some match. There would still be other sources because the parameterization, it's not a single parameter system, really. And there's of course, these are all calculated approximating or assuming that this was a good approximation from the derivative, which is really not the case for the faraway ones, which is why these are all radii that we have a lot of points close together around from the range of simulations we've done.
So whether you use radius or
Oh.
same underlying family?
Yes. Yeah, I'm sorry, I flipped.
The same one.
Yeah, I should have used. Yeah, so so since lambda is basically some small coefficient times radius to the 5th power, they are mostly degenerate. They are very slightly different. It's just a slight skew in the shape. But given the set of equations of state, you can choose either one at this point fairly equivalently. Lambda has the advantage that you can compare to these post-Newtonian things and see what you would expect, where the waveform variation is really described by that parameter. Okay, any other questions? Okay. So this is really nice because actually doing a much better calculation where we actually did numerical systematics in a more explicit estimate, we get results that agree fairly well with our original estimates. At least our order of magnitude wasn't off. So that's good. They're not. You can't really compare them directly since these are using slightly different frequency ranges, but regardless. Okay. I would also like to say a little bit about, okay, so we have these spikes, and something particularly interesting is, well, the cold equation of state is a good description of the in-spiral. As soon as they smash together, they do a lot of messy and interesting stuff. And this is probably not going to be well described by a single parameter like lambda. Although perhaps the frequency of these peaks can be related. But regardless, so the question then is, are these going to be themselves independently detectable? So if we take only the portion of the waveform after that in-spiral, after they smash together, so you see either you have these little blips of the black hole ring downy-like stuff, or you have these post-merger oscillations, and then you can sort of say, well, for the length of time we simulated, which was tens of milliseconds, this is something that you can see in ET, but not really in advanced LIGO. But they are quite different, so that you could imagine having some additional information to distinguish matter properties based on this kind of observation in a third-generation detector. There's a caveat that these are very dependent on the stability of the post-merger oscillation object. So this is something that eventually viscosity or magnetic braking, probably magnetic braking, is going to kill, and that's not in our simulations. What people think the length scale of this can actually be, where it varies wildly, and this is also something, the time until a sudden collapse is not convergent in the simulations, not surprisingly. So this is something interesting that is an interesting scenario to consider going forward, although unfortunately even in the broadband advanced LIGO configuration it's probably not going to be visible, at least this first estimate, or second estimate. There's some previous work done on this, of course. Okay, so I have 5 minutes left, so let me just talk very briefly about kind of the obvious next step is to try and link these two together explicitly. So there's this modified p-in waveform measurability estimates that said things were indistinguishable. And then, but with the numerical simulation, they were distinguishable. And the obvious thing is that this is restricting ourselves to information below 450 hertz, and this is restricting ourselves to information above 500 hertz. And the reason we cut off this is because there are other high frequency effects, and this we are constrained by the start of the numerical simulation. So the idea would be to construct hybrid waveforms. And the interesting thing is if you do a very preliminary rough, many things could go wrong. If you do this, if you basically extend your post-Newtonian arbitrarily and just match extend the post-Newtonian with first-order corrections arbitrarily and match a numerical simulation onto it, you get SNR of differences which is quite a bit larger than you got with numerical simulation alone, and it's actually larger than the addition of the two regions independently. That additional SNR of difference is really coming from the matching region. So ironically, the region that we know less about, or the least about, in terms of having a confident description of the waveform, is the one that's most significant for measuring the difference between two So the idea then is we want to push the post-Newtonian description more accurately into higher frequencies, and Tanya has informed me that the next to leading order contribution is almost entirely calculated and amplifies the tidal correction even. So this is an exciting thing to contribute. And then of course you want ideally to have some region of robust overlap where you can confirm that the two methods are describing the same system, which we do not yet have. And numerical error increases going back to lower frequency. So this takes some delicacy and actually making sure you do all the numerical waveform extraction things properly. Which this, by the way, does not do. So there are tons of systematics here, but at least in terms of the difference in broadband advanced LIGO being, say, up to 10, well, for the extreme, probably unrealistic case, but in any case, quite sensitive, say, to the distance and difference in radius, I think this is definitely something that we should devote attention to as a scientific community in the next few years. So thank you very much.
You had a graph where I think you showed shaded regions and one was labeled NPE matter only.
Oh, yeah, sorry.
If there were some more body matter, what
Okay, so the NP mu matter only is the selection of the equation of state lines that I've plotted here. It's in the paper that this comes from, which is the archive 09113535. We also include the same plot, which has the same advanced LIGO and Einstein telescope lines, but different equation of state lines that come from strange quark matter as well as matter with kaon condensates and various other interesting things. They do not, quark matter tends to be small, lambda. There's no real consistent way you can differentiate categories just simply based on lambda. It's similar to mass radius. You have a different shape to the line. The astrophysical constraints probably translate to something between 2 and 5 in the key region. You can put any equation of state or property you want in here and see what lambda is as a function of the mass. That's not only NPU matter that's possible. Those are just the ones I plotted.
reasonable. I mean, that basically just the time that you have to simulate.
Yeah. Well, the binary simulations are, the most recent ones are already going down to about 500 hertz. And I think with the next to leading order tidal contributions, we can probably have a pretty, since that was the leading reason that we cut off at 450 hertz was the next to leading order tidal potentials that are now all calculated.
Is it the octopole next to it?
Yeah, so next to leading order, it's two parts. There's the octopole deformation with the leading tidal potential. There's also the post-Newtonian tidal potential adding to the quadrupole deformation. So there are two components, and the more significant one is the next to leading order tidal potential contributing to the quadrupole deformation. The nice thing is that is the same parameter, lambda, just with an amplification as a function of frequency due to the non-Newtonian tidal field.
So how many orbits?
Well, it depends on the equation of state, but about that many. Well, yeah.
So
neutron to find that?
It can be simulated. The accuracy is key. Because you want to simulate, the problem is that the lambda contributions are quite small over this whole range. They're, fractions of a radian, and to get the numerical accuracy down to fractions of a radian is difficult. And the other issue is, since you have to do some alignment procedure, there's a freedom to slide things back and forth relative to each other. And especially in the early part of the waveform, where the difference in frequency the frequency sweep as a function of time is pretty flat, it's really easy to slide two almost flat things against each other without making large differences. So yeah, it's not. I mean, I would be surprised if we don't have this solved in 5 years, but it's not going to solve itself. So. Yeah, so the numerical simulations, the physics is all in there. The physics relevant for the in-spiral. For the in-spiral, I believe so. I mean, for the in-spiral, before the neutron stars crash into each other, there's no heating. They're still ground state objects. Do you disagree? That, I think, is very small. Okay.
But that hasn't been.
Yeah.
Is there viscosity?
No, that's perfect field. The timescale of viscosity is such that I think it's not going to contribute. Although, given the length, viscosity isn't enough to tidally lock them over their whole orbital in spiral. So I don't think it's going to be something that. These are all things that can definitely. A lot of these things were originally looked into from the perspective of detection with initial LIGO. And now that we're thinking about doing parameter estimation with advanced LIGO, and systematics are much more important, there are a ton of things that you can go back and check more carefully with the current technology, just to see if we're tripping things up. Because I don't think we really expected this amount of tidal effect when or not, at least not everyone did. 5 years ago, because if you look in the region for initial LIGO, and for detection, tidal deformation is insignificant. It's only when you have the broader frequency band of advanced LIGO that this becomes a few percent that you can potentially start seeing.
And my question here is, from an instrumental point of view, because we have some instrumental, where would you want to see the real energy? With the lower frequency part?
Broadband, yeah, high frequency.
High frequency?
Yeah.
Right, thank you.
No, yeah. That was a setup, yeah.
But, well, thank you very much, Jocelyn, for that very nice